Welcome back. Over the past 200 years, some of the world's most innovative structural systems have been developed in response to the need for roofs over large, uninterrupted public spaces, like markets, transportation facilities, stadiums, and arenas. This function, spanning long distances with no interior columns, is structurally very demanding. And so a wide variety of innovative structural forms have developed in response to the challenge. One such response is the thin concrete shell, which we examined last lecture. Concrete shells offer unique opportunities for architectural expression, as we saw, and they've also proved to be quite economical, particularly in times and places where relatively low labor costs allow for the complex temporary formwork to be constructed without breaking the project budget. But in recent decades, the cost of labor in the West has been relatively high in comparison with the cost of materials. And so there have been relatively few new developments in thin shell structures during this period. Indeed, this seemingly simple concrete shell that I showed you last lecture to demonstrate the high-par roof structure was by far the most challenging and most time-consuming of all the demonstrations I put together for this course. A pretty good indicator of why simpler iron and steel frameworks have continued to be the structural systems of choice for the largest and longest spanning roof systems during this same period. In much the same way that the world's longest bridge spans have been iron and steel structures over the past 2 centuries. In today's lecture, we'll look at the development of long-span iron and steel roofs from 1800 to the present. In doing so, we'll discover a fascinating phenomenon. Successful long-span structural configurations don't ever seem to go away. They evolve, they're refined, sometimes they fall out of fashion for a period and then they're rediscovered, but as it turns out, many groundbreaking long-span structural configurations of the 19th century are still used in some of our most modern structures today. I've used this observation as the basis for organizing today's lecture. We'll look at a variety of different long-span structural configurations, and for each one, we'll examine at least one great structure that's quite old and at least one that's relatively new. In comparing the old and the new, we'll see both continuity and change. Let's begin with a structural configuration that's been used to enclose large spaces for thousands of years, the dome. Thus far in the course, we've seen the ancient stone dome of the Treasury of Atreus at Mycenae, the monumental concrete dome of the Pantheon in Rome, brick domes over the Basilica of Hagia Sophia in Constantinople, the Cathedral of Santa Maria del Fiore in Florence, and St. Paul's Cathedral in London, and a variety of 20th century thin shell domes in concrete and ceramic tile. Today we'll look at domes that are not solid masses of masonry, but rather open frameworks of iron or steel. The earliest of these, and indeed the world's first long-span iron roof, was the dome of the Paris Grain Market. This circular building was originally covered with a wooden roof, but when that wooden structure burned down in 1802, François Bélanger designed a 128-foot diameter replacement made entirely of iron and sheathed in copper, as you can see here. Bélanger's dome is a hemisphere, framed as a grid. Now, recall that the elements of this grid that we use to define directions in a dome are called meridians and parallels. Each meridian forms a semicircular arch that passes through the central axis of the dome, and each parallel forms a horizontal circle centered on the dome's axis. In masonry and concrete domes, these meridians and parallels are imaginary lines that help us visualize internal forces. But in the Paris Grain Market, this grid is real. As you can see here, it's composed of iron structural elements. Cast iron for the meridians and wrought iron for the parallels. Let's use a model to review how a dome carries load. This is the same model that I used to talk about domes some lectures ago, and it's made up of a series of meridional slices, that is, segments of the dome that are aligned with the meridians. Remember that when this dome is subjected to load, the meridians act like arches. They carry load in compression, and under load they spread outward due to the lateral thrust, very similar to the way an arch behaves. As those meridians spread, they move farther apart. Note that the gap between the meridians gets larger. That spreading apart corresponds to tension in the parallels. And that tension has a name. We call it hoop stress. If the parallels are capable of carrying tension, then we saw that the dome is actually capable of carrying substantial load without any external lateral support at all. However, even if external lateral support is provided, the hoop stress doesn't go away. In fact, under load, those meridians still continue to spread apart, which simply means that the hoop stress occurs somewhat farther up from the base of the dome. Again, though, as long as the material that makes up the parallels is capable of carrying tension, then the hoop stress is carried by those hoops. Now, in the Paris grain market, the meridians, which carry load in compression, are made of cast iron, while the parallels, which carry load in tension, are made of wrought iron. So Bélanger's choice of materials was actually quite well suited to the structural behavior of the system. The elements carrying load in compression were made of a material that's quite strong in compression, even though it's weak in tension. And the elements of the system that are carrying load in tension are in fact made of the material wrought iron, which is stronger in tension. Now, based on this demonstration, we can see that an iron frame dome carries load in fundamentally the same way as a masonry or concrete dome, though the frame dome is actually somewhat easier to understand because the load paths are more explicitly defined by that iron grid. The historical transition from solid domes in masonry to iron-framed domes closely parallels the transition from solid masonry walls to iron-framed structural systems in buildings. And it happened for many of the same reasons. It resulted in significant reductions in weight, just as the size or thickness of masonry walls got thinner in response to the transition to iron and steel frameworks. So the weight of a dome gets substantially less when it transitions to an iron framework. It also resulted in greater strength in response to non-uniform loads like lateral wind load applied to the structure, as well as greater opportunities for providing larger window openings within the structure. The structural efficiency of the Paris grain market dome is really quite remarkable. It weighs 220 tons, which works out to about 34 pounds per square foot of floor area covered. Now, in comparison, the inner shell of Brunelleschi's brick dome in Florence weighed in at 700 pounds per square foot. That's 20 times higher. And that's only for the inner shell. Remember that Brunelleschi's dome was two shells, an inner and outer, and both were essential to the structural system. In the 1880s, the grain market was converted to the Paris Bourse de Commerce, and the copper roof sheathing was replaced with glass, as you can see here. An architectural embellishment that wouldn't have been conceivable with a solid masonry dome. The original 200-year-old iron framework remains within this great building for us to admire today. Now let's look at a modern framed dome. The Houston Astrodome, constructed in 1965, was the world's first domed stadium. At the time, it was heralded as the eighth wonder of the world. The title may seem a bit overstated today when many larger and more impressive stadium roofs have been built, but it does give us a good sense of just how unprecedented a roof system of this size was just 50 years ago. In the early 1960s, baseball's National League was expanding, and Houston wanted a team. The league would grant a franchise only on the condition that the owners build a covered stadium. The league's assumption was that a baseball franchise could only be economically viable in the subtropical climate of Houston if spectators were protected from sun and rain. One of the owners, Roy Hofheinz, first conceived of a domed roof and was the driving force for building it. Hofheinz, a flamboyant former mayor of Houston, claimed to have gotten his inspiration from a visit to the Colosseum in Rome. There he learned about the huge fabric awning called a velarium that was stretched over the Colosseum seating area to shade the spectators. And so the old inspired the new. And by the way, we'll be inspired by the velarium again next lecture. The Houston Astrodome spans 642 feet, and its apex is 208 feet above the playing field. The shape is spherical, but as you can see, it's only a thin slice of the top of a sphere. Recall that the main dome of Hagia Sophia in Constantinople used this same shallow spherical configuration to minimize hoop stresses. Now, at Hagia Sophia, this proved to be problematic because a flatter dome generates considerably greater lateral thrust. But in a modern steel structure like the Astrodome, thrust is handled quite easily by a circumferential tension ring at the base. The actual structure of the Astrodome is a geometrically intricate steel framework, as you can see here. It was designed not only to carry its own weight, but also to withstand hurricane-force winds. But on closer examination, we can see that this complex structure actually works in exactly the same way as the dome of the Paris grain market. These parallels fulfill exactly the same purpose as the wrought iron parallels in the Paris dome. The hoops still carry hoop stress. And in place of the cast iron meridional ribs, the Houston dome uses a series of alternating diagonals that perform the same function, but with the added rigidity that comes from the triangular shape. And so, even though the Houston Astrodome was the world's first domed stadium, it was very much a mainstream structure. It employed no new technologies or major structural concepts. Sometimes, as they say, there's nothing new under the sun. Slight pun intended. Today, the eighth wonder of the world has become functionally obsolete, and it's been replaced by two new retractable roof stadiums, though the dome itself is still more than adequate structurally. In a few minutes, we'll see how the need for a retractable roof can dramatically influence a stadium's structural system. But first, railroad stations. The early railroad stations of the Industrial Revolution are sometimes called the cathedrals of the 19th century. Public spaces that reflected the technological prowess of the era. Given Britain's pioneering advances in both railroads and iron structures, it's hardly surprising that many of the great early station structures can be found in London. The original roof over the passenger platforms at London's Euston Station, built in 1837, was supported on some of the world's earliest iron trusses. As you can see, each truss was fairly short in this case, spanning only two sets of tracks and one platform. But 30 years later, the state-of-the-art had advanced considerably. St. Pancras Station, built in 1868, included a train shed with a glass-covered iron canopy that spanned 243 feet, then the longest single-span roof in the world. The main structural elements, as you can see here, are trussed arches, similar to the Eads Bridge and the Garabit Viaduct, both of which were built during this same era. The arch was 100 feet tall to allow for the venting of steam from the locomotives of that day. Not only has this great Victorian-era train shed survived, but it's actually been incorporated into the passenger terminal used by the modern Eurostar trains that run through the Channel Tunnel between England and France. These beautiful, historic iron arches and the sleek trains located below them provide a wonderful juxtaposition of old and new technology. Now that we've seen long spans in old stations, let's visit Europe's largest and most modern train station, the new Berlin Hauptbahnhof. This is a magnificent structure consisting of two huge glass-covered vaulted train halls intersecting at right angles and integrated with two 12-story office buildings. The vaulted roof of the east-west train hall is particularly fascinating. The principal structural element here is a lightweight arch with a very flat profile that the designers call a basket handle arch. The span is about the same as that 19th century train shed at St. Pancras, but it's only about half the height. Of course, providing space to vent steam from locomotives was no longer a consideration in the design of this modern station. The arches at St. Pancras are trusses, and if you look closely, you can see lightweight trusses integrated within the Berlin station's arches as well. Viewed from the outside, we can see these trusses extending outward near the ends of the arch. Now, this 3D model shows the complete system. The basket handle arch, reinforced with an internal truss hanging down below the arch in the center, and two external trusses extending above the arch out near the ends. Why this strange configuration? Well, note that even under uniform load, a flat elliptical arch like this one tends to bend significantly. It flattens out in the middle and it bulges outward at the ends. If we draw the moment diagram for this arch, that is, the graph of the variation of internal moment along the length of the arch, it looks like this. Notice that the moment diagram is exactly the same shape as the truss. And so this strangely shaped truss is actually perfectly tuned to its load-carrying purpose, a beautiful integration of form and structure. Now let's look at a fundamentally different type of long-span truss. Until the end of the 18th century, virtually all iron and steel trusses were designed in two dimensions. Structural systems like St. Pancras train shed were visualized, modeled, and designed as a series of planar elements. During that era, this approach was essential because the available computational methods didn't permit the analysis of more complex structural geometries. Planar structures reflected the available analysis tools, which really were only effective in two dimensions. But in the 1930s, a German engineer named Max Mengeringshausen began experimenting with three-dimensional truss configurations like this one. Structures that couldn't possibly be visualized or analyzed as a series of discrete parallel elements. Today, these configurations are called space trusses because their geometry is defined in three-dimensional space rather than a two-dimensional plane. Mengeringhausen's intent was to create a standard kit of parts that could be assembled into complex structures. And the key to this system was the connections. Mengeringshausen invented a steel node with threaded holes allowing up to 18 members to connect together from different directions, as you can see in this graphic. He then mass-produced steel rods that could be assembled with these universal connectors to make full-fledged structural systems. Called the Miro system, Mengeringhausen's modular structural components led to a significant increase in the use of space trusses. And Mengeringhausen's company is still in business today. It's called Miro Structures, and that company's building space trusses for a wide variety of structures. Here's a particularly interesting one. The National Performing Arts Center of Singapore, completed in 2002. This incredible curved exterior is one immense space truss, a wonderful demonstration of the Miro system's versatility. When we look at this ultra-modern structural application, it's hard to believe that we're actually looking at a structural technology that dates from the 1930s. Well, with the success of the Miro system and the advent of computer-based structural analysis methods, the use of space trusses became increasingly popular around the world. And so when the city of Hartford, Connecticut needed a new civic center in the 1970s, the space truss was the natural choice for its long-span roof. The structural system of the Hartford Civic Center was both innovative and daring. The roof was a single space truss measuring 300 feet by 360 feet and supported on just 4 columns, as you can see in this 3D model. The truss was composed of a rectangular grid of interconnected modules, each shaped like an inverted pyramid. The roof structure consisted of 120 of these modules, 10 in one direction and 12 in the other direction. So you can see that the modules themselves measured 30 feet by 30 feet. This complex geometric arrangement of slender elements was intended to produce a startling architectural effect, a light, delicate roof that would appear to float high above the thousands of spectators seated in the arena. Here you see a model of 4 of the modules of the Hartford Civic Center roof truss. And this model nicely illustrates the complex three-dimensional geometry of a typical space truss. You can see that it's composed of 4 of these inverted pyramid-shaped modules. Here's the inverted pyramid. And they're combined together in a grid pattern to form a complete three-dimensional truss. What you need to recognize, though, is that even though this truss is so unconventional in terms of its geometry, it still carries load like any other truss, like the two-dimensional planar trusses that we looked at on a number of occasions earlier in the course. When it's supported on its columns and extended out across a large expanse of space, The top chords of this structure experience compression, and the bottom chords of the structure down here experience tension. You may also notice on the structure these short vertical posts that extend from the joints that connect the top chord members together. Those posts were actually used to support the concrete roof deck that rested on top of the structure, just like this. These posts were actually considered to be a particularly innovative design feature at the Hartford Civic Center because they facilitated the process of building the roof deck at the correct elevation with the very slight curvature that's necessary to ensure proper drainage on any roof. Now, normally this curvature would be achieved by configuring the lengths of each individual member of the truss in order to cause the truss itself to assume a slightly curved shape. But on the Hartford trusses, this effect could be achieved much more cheaply by simply adjusting the lengths of those vertical posts. But the posts had a significant disadvantage. As you could see in my model, they physically separated the top chord of the truss from the concrete deck. We'll see why this was important in just a moment. On January 18th, 1978, in a moderately heavy snowstorm, the roof of the Hartford Civic Center collapsed catastrophically, with no warning whatsoever. The human cost of this failure might have been staggering. Just 6 hours earlier, the arena was filled with nearly 5,000 spectators watching a college basketball game. Luckily, the roof fell at 4:19 a.m. when the building was completely empty. In the investigations that followed, a number of factors were found to have contributed to the collapse. The designers had actually underestimated the dead load of the roof by about 20%, and there were some problems with the geometric configuration of the truss connections. But neither of these errors was sufficient to have caused the collapse. To understand the main cause of the failure, let's return to our model of the truss. Now recall that on this space truss, the top chord members are loaded in compression. What happened was that these top chord members buckled. Why did it happen? Well, the top chord members were designed to resist buckling by the design engineers, but the unbraced length that was used as the basis for the buckling calculation was 15 feet. That's this distance right here, half of the total width of the 30-foot module that defines the pyramid shape of the truss. Why did they use 15 feet rather than 30 feet? Well, as you recall from our lecture on compression members and columns, providing lateral bracing on a column is a legitimate way to increase its strength. Remember that the length of a column is contained in the denominator of the Euler buckling equation, and therefore decreasing the length significantly increases the strength of a compression member. The designers recognized that even though the width of the module was 30 feet, these two diagonal members framed into the middle of the top chord at the 15-foot mark, therefore dividing the chord from its original 30-foot length into two 15-foot lengths. The designers assumed that these lateral bracing members would provide adequate bracing so that the strength of the column would be defined in terms of buckling with respect to the 15-foot length rather than the 30-foot length. Now, it turns out that that assumption was exactly correct for the internal compression members, the interior members, the ones that run, for example, in here and in here on the inside of the modules of this truss. And that assumption was correct because in these circumstances, there are actually 4 bracing members that connect into that center node. Now, recognize that under axial compression, this compression chord tries to buckle outward. In order for it to buckle on the 30-foot length, this top chord joint would need to displace sideways as the top chord buckled. Of course, because these bracing members are coming at the joint from 4 different directions, it's impossible for that joint to displace laterally. It is, in fact, stable, and the assumption of a 15-foot unbraced length was completely appropriate as a result. But out here on the outer perimeter of the truss, the same sort of compressive load also causes a tendency for this compression member to attempt to buckle across the entire 30-foot length. But now, because there are only 2 diagonal members, it is much easier for this joint located in the middle of the compression member to displace sideways under that compression load. And if that joint is able to displace sideways, then the lateral bracing isn't adequate to restrict buckling to the 15-foot unbraced length. Well, let's see if I can actually displace this top chord joint laterally. In fact, I can. You can see that with some modest amount of pressure, I can cause that top chord joint quite easily to move sideways. And it was precisely that lateral movement that caused the failure of the Hartford Civic Center roof trusses. The top chord members buckled on the 30-foot length rather than the 15-foot length, and as a result, the disaster ensued. This seemingly simple oversight, the designer's failure to recognize that the top chords weren't properly braced, resulted in those members being overloaded by 400%. It's a wonder that they didn't fail sooner. And by the way, if the concrete deck had been built directly on top of those top chords, the deck itself would have provided the sort of lateral support that would have prevented this buckling from occurring. But those innovative vertical posts separated the deck from the truss, and therefore the deck wasn't able to provide the needed stability. How could this sort of oversight possibly happen? Well, first, in the 1970s, computer-based structural analysis methods were still quite new. Computer models could be used to calculate the internal forces in the members of a space truss, but they weren't capable of evaluating three-dimensional stability. That evaluation required human judgment. And because the engineers who made that judgment were schooled in the traditional two-dimensional analysis methods in the engineering school system, they weren't able to visualize the three-dimensional behavior of this unique structure that they were designing. You know, in this course, we're learning to see and understand structure. Seeing and understanding structure is precisely what the designers of the Hartford Civic Center Space Truss failed to do. The result was disastrous. This cloud does have a silver lining, though. Like so many previous structural failures, the Hartford disaster has led to improved understanding of structural behavior, and as a result, sophisticated and safe 3D space trusses like the Singapore Performing Arts Center are now quite common. But as modern long-span structures go, there are few more impressive than the new University of Phoenix Stadium, which opened in 2006. The design for this stadium called for a retractable roof as large as the playing field and capable of being retracted lengthwise toward the end zones. The resulting structural system features two immense steel trusses running the full 700-foot length of the stadium, supporting the outer edges of that retractable roof. These are no ordinary trusses. Indeed, each one might be regarded as a structural system in its own right. Their overall shape is lenticular or lens-shaped. Because of this shape, the system works essentially like an arch and a cable combined. The curved bottom chord is made of two heavy steel eye-shaped members, but it functions just like a draped cable in tension. And the curved top chord works just like an arch in compression. Because these two elements are connected at their ends, the compression and the tension counterbalance each other, and so the structure as a whole generates no lateral thrust at its supports. Note that the top chord is actually a full three-dimensional truss in its own right, a box composed of four heavy eye shapes interconnected by diagonals, resulting in a structure that provides the necessary strength and compression while also preventing the sort of lateral instability that caused the Hartford Civic Center collapse. The uprights connecting the top and bottom chords together actually form a series of triangles, giving the structure even more rigidity in the lateral direction. And finally, recognize that these simply supported trusses have essentially the same shape as the parabolic moment diagram of a simply supported beam, as we saw back in our lecture on flexure. And that's why those innovative iron beams at Orrell's Mill have this parabolic profile. We've seen on many occasions that trusses carry load essentially like beams, and so it makes perfect sense that the optimal shapes for a beam and a truss are essentially the same. The roof system of the University of Phoenix Stadium is a highly sophisticated reflection of modern structural engineering know-how, and yet its configuration is nearly identical to the main trusses of this bridge, the Royal Albert Bridge at Saltash in the UK, built in 1859. The Royal Albert Bridge was designed by an extraordinary British civil engineer named Isambard Kingdom Brunel. Note that the Royal Albert Bridge uses the same lenticular shape as the University of Phoenix roof trusses. The individual elements are different. The top chord, the arch, is a heavy iron tube rather than a box truss, and the bottom chord is made of draped I-bar chains, similar to the ones used in modern suspension bridges of that era. But the structural system works in exactly the same way. Kudos to Walter P. Moore, the structural engineer of record for the Phoenix Stadium roof, for giving credit where credit is due. In all of the publicity surrounding the construction of this great structure, those magnificent roof trusses have been called Brunel trusses, an honorific that reflects both historical awareness and professional respect for one of the most accomplished engineers in history. Again, the old has inspired the new. During this lecture, in examining some representative examples of large and long-span roof structures, we've seen once again how the challenge of building across long distances and enclosing large areas has stimulated structural innovation. Sometimes innovation is manifested in new structural configurations. Sometimes it's manifested in new or more ambitious implementation of older ideas. In either case, innovation inevitably involves the use of untried technologies or methods, and thus always involves some risk. In the Hartford Civic Center, risk turned to disaster because the engineers were looking at a new structural configuration in an old way. But the more inspirational side of our story is found in the many cases where designers looked at old structures in new ways. The engineers and architects of the Houston Astrodome, the Berlin Hauptbahnhof, the Singapore Performing Arts Center, and the University of Phoenix Stadium were able to see the great structures of yesterday and envision new possibilities for the great structures of tomorrow. Next lecture, we'll see a revolutionary new form of long-span roof, the tension structure, which also derives from an ancient precedent. Until then, thank you.